Okay, everybody, in my last video, we went over the quick and easy way to just memorize the graphs of sine of x, cosine of x, and tangent of x. In this video, we're going to discuss the graphs of cosecant and secant. And so what I'm saying, I guess, is this right off the bat. The fact of the matter is this: if you want to graph cosecant and secant, essentially what I'm going to tell you is, and those lines were very ugly, cosecant and secant, basically all you need to know how to do is graph sine of x and cosine of x, because these functions will be the reciprocal functions of sine and cosine. So if I know what sine looks like, I can graph its reciprocal. If I know what cosine looks like, I can graph its reciprocal, which are cosecant and secant respectively. So let's go ahead and start with y equals cosecant of x. Now what I just mentioned was this: if you can graph y equals sine of x, then we can graph cosecant of x. Let's go ahead and get started with this. What do we know about the graph of y equals sine x? Well, its period is 2 pi. It's 2 pi. And its amplitude, this number out front here, and I haven't discussed this yet in my videos, but its amplitude is 1. Amplitude equals 1. Okay, so anyways, let's go ahead and sketch out our graph here. Essentially, we know that since its amplitude is 1, it's going to go 1 above the x-axis and 1 below the x-axis. We say we're graphing sine here. So since the period is 2 pi, we'll go out 2 pi units past 0. This is the quick way of graphing this. We'll split that in half, okay, so that's pi. We'll split those halves in half. We'll just quarter it. And so what do we know about sine? Well, we know sine starts at the ground level, okay, goes up to 1, a fourth of the way through its period, goes back down to the ground level, half of the way through its period, is down at -1, its minimum, 3/4 of the way through its period, and then a full way through its period, it is back up at the ground level. So this is the graph of sine of x, ladies and gentlemen. Okay, so what we want to do is graph the reciprocal of sine, which is cosecant. So now we need to have this conversation. I know I didn't make a table of values to plug into cosecant, and that's something we could do. As a matter of fact, you know, you could go back and find x, y, plug in like 0, pi fourths, you know, pi fourths, pi halves, you know, 3 pi fourths. You can do that and plug that into cosecant, and you're going to have to find the sine values anyways. But we say, okay, so what's the sine, the value of sine at 0? Well, was at a height of 0. What's the reciprocal of 0? Isn't that undefined? I think it is. So here's what I know. Whenever the graph of sine of x is at a height of 0, then its reciprocal function is going to be undefined at those spots. What does this mean? It means that our reciprocal function is going, or cosecant in this case, is going to have asymptotes wherever the original sine graph was at a height of 0, because the reciprocal of 0 is simply undefined. So how, you know, what other points would exist, say, for example, on my cosecant graph? Let's switch over to like light blue here, azul. Basically, we could say, oh, well, you know, I know that a fourth of the way through my sine graph, it was up at a height of 1. What's the reciprocal of 1? It's also 1. Okay, easy point to find the reciprocal of. How about 3/4 of the way through its cycle? It was at a height of -1, my sine graph was. What's the reciprocal of -1? It's also -1. Okay, so what I know is those points in purple and in light blue exist on both of these graphs here, because the reciprocal is itself. So what about some other points? Well, here's what I can tell you. Essentially, the smaller and smaller, so like for example, look at your sine graph, is its y values are getting smaller and smaller and smaller and smaller and smaller and smaller and smaller, approaching a height of 0. What you should know is this: then its reciprocal function would be getting larger and larger and larger and larger and larger and larger. Because when you flip over proper fractions or very, very small numbers, you reciprocate those, they get very large. Okay, so again here, you know, like what if my sine graph, its y values are getting smaller and smaller and smaller as it approaches a pi radians, then its reciprocal would be getting larger and larger and larger and larger and larger and going this way. Okay, so that's the left half of our cosecant graph. What's the right half look like? Well, it goes through -1 right here, of course, right at this point. But we say, okay, so as these x values are getting smaller and smaller and smaller, well, at least approaching 0 in their size, then its reciprocal function would be getting larger and larger. It's just that this time, these reciprocal values, hey, if you take the reciprocal of a negative number, then its reciprocal is also negative. So basically, this graph in blue right here is the graph of one period of cosecant. So one important thing to note about cosecant here is this: it also has a period of 2 pi. Why? Because its reciprocal had a period of 2 pi. It took the sine graph 2 pi's worth of input degrees or radians to go through one complete cycle, it takes our cosecant graph one whole 2 pi period to go through one cycle. Well, it looks like it's split up into 2 different parabolas. First of all, these are not parabolas. And second of all, it did take 2 pi to go through one cycle because it needed its reciprocals up here and it needed its reciprocals down here. And then it would indefinitely just repeat itself over and over and over and over again. Okay, so now let's explore the graph of y equals secant x. So y equals secant of x. Well, I'll tell you what, if you wanted to graph y equals secant x, what I'm telling you is you just need to know how to graph y equals cosine of x. So y equals cosine of x. What do we know about cosine? Cosine, in this case, it's 1 times cosine of x, so it has an amplitude of 1. But essentially, it's going to go 1 above and 1 below the x-axis. Okay? It has a period of 2 pi, so it goes out to 2 pi. So here's its period from 0 to 2 pi. Again, the quick and dirty graph is just this. Go out one period past where you're starting, split that in half, okay? Split those halves in half, and now we've quartered this up, okay? So what do we know about cosine? Cosine starts at a height of 1. A fourth of the way through its period, it's down at ground level. When it's at a half of the way through its period, it's down at -1. You just memorize it, okay? 3/4 of the way through its period, it's back up at 0 again, a height of 0, ground level. And then it ends back up at 1 again. That is, it took 2 pi's worth of x values to get it to go through one complete cycle of y values. All right, so what if I wanted to graph the reciprocal of this? Well, just like over with sine, whenever sine was at a height of 0, like there and there and there, we had reciprocal values that were undefined. What you should know about the graph of secant of x is that it's going to have asymptotes wherever the graph of sine was at a height of 0, because if you try to reciprocate 0, you get something that is undefined. What would the rest of this graph look like then? Well, I think we should switch colors probably again, maybe over to like a green. That would contrast well. So we say, okay, so like right here on my cosine graph at 0, x equals 0, we say the reciprocal of 1 up here would be 1 itself. Over here at pi, my original cosine graph was at a height of -1. So its reciprocal is also at a height of -1. And at 2 pi, my cosine graph is back at a height of 1. So its reciprocal is at a height of 1. So now, as cosine, let's say if we start getting closer and closer to this x value here, as its y values are dropping off, its reciprocal values then would actually be getting larger and larger and larger and larger and larger. Approach this asymptote, never touch it. Again, down here, we had the original cosine values were below 0, they were negative. So as they get smaller and smaller in size and magnitude, its reciprocal values would be getting larger and larger. So basically, you're going to look at a graph here of secant that looks a lot like cosecant. It really is. It's just kind of staggered to the right or left a little bit, however you want to interpret it. But basically, cosecant and secant, I look at them this way. They're just graphs that are undefined where their reciprocal functions are at a height of 0. So at heights of 0, like here and here, they'd be undefined, or sine, cosecant would be undefined there, there, and there. And then they just kind of like touch their butts on the original graph of sine or cosine, respectively, and then proceed off to either positive infinity or negative infinity. So that's the quick and dirty version of how to graph cosecant or secant. So just as kind of an amendment to this video here, what you can see here in GeoGebra is a graph of y equals sine of x. You can see that up over here. And we're about to highlight y equals, or g of x is, cosecant of x. But just to show you how these reciprocals behave, you see that sine, of course, here's our 0 to 2 pi period here. And you notice that wherever sine is at a height of 0, when we graph its reciprocal, our reciprocal function is going to be undefined. So let's take a look at cosecant here. You notice that cosecant is just, it's got these little, they look like parabolas, but they're not, these little u's, okay, that touch their butts on the original, graph of y equals sine x at their little humps there. But whenever the original sine graph was at a height of 0, you would see that our graph doesn't necessarily walk there. Our cosecant graph is undefined at those spots. So we can actually zoom out here, and you'd see that cosecant is just a series of, as the sine values are getting closer and closer to 0, they get closer and closer to either positive or negative infinity, and they just basically touch the graph tangent at those humpy spots. And then whenever the original sine graph is at a height of 0, we'd have a cosecant graph that's undefined. Okay, so what would be different? What would be different about, say, cosine? Well, if I zoom back in here, we say here's our 0 to 2 pi period there. And let's say y equals cosine of x. There she is, starts up at 1, goes down, and then down at -1, back up to ground level, and then back up to 1. If we were to graph now y equals secant of x, it also does the same thing like cosecant did. Whenever the graph of cosine was at a height of 0, we had a graph that was undefined. So all of these spots where our cosine graph was on the x-axis, we have cosecant graphs that weren't there. They were undefined. And also, we can see that the secant graph comes up and touches the cosine graph at that one spot where it's at its minimum or maximum, and then proceeds off to either negative infinity, as in the case below here, or positive infinity, as in up here. But it also has a period of 2 pi because it takes it 2 pi's worth of rotation to go through one full cycle.